Last week, we introduced this BCS theory of superconductivity for ordinary metals, and we apply the assumption and approximations made by the BCNS, by the Cooper and Schiffer, and they assume that this gap, BCS gap function delta, or the Cooper pairing, or the parameters, takes the mean field value when temperature is less than Tc, and it is just constant, so so-called S-wave pairing, because delta is isotropic in momentum space, so it takes the spherical shape of sphere, and that's why we call this S-wave pairing. And for the S-wave pairing, this BCS Hamiltonian can be expressed in terms of this 2x2 matrix in the so-called Nambu basis. Remember, last time we derived such a matrix representation of the BCS Hamiltonian, and so the remaining task is to find these eigenvalues and eigenvectors of this Hamiltonian matrix, and it is easy to find because it is simply just an exercise to find these eigenvalues, and you could take advantage of what you learned in applied math. By unitary transformation, you could diagonalize the matrix. And such a unitary matrix is given by this 2x2 matrix with the matrix elements UK minus VK and VK star and UK star. And this coefficient UK and VKs are called coherence factors. Later we will interpret these coherence factors in more details. Namely, so these coefficients can actually help us to diagonalize this 2x2 BCS Hamiltonian and find eigenvalues. And eigenvectors are nothing but this 1x2 or 2x1 column row matrix made of this matrix elements of this unitary matrix U. So for the positive eigenvalue Ek, where this Ek is square root of this epsilon k minus mu square plus delta square, and the eigenvector is Uk minus Vk, and for this minus eigenvalue minus Ek, the eigenvectors is given by this Vk star and Uk star. The star refers to the complex conjugation. Okay, so we will analyze this so-called Bogoliubov quasi-particle excitations in more details later, but let's just define this Bogoliubov quasi-particle operators. As I mentioned, by unitary matrix U, you can form a linear combinations of a C and C dagger with the opposite momentum k minus k and spin up and down, so that the Hamiltonian matrix is diagonalized. So such the operator made of this linear combinations of C and C dagger is called Bogoliubov quasi-particle, and we have a notation gamma with the momentum k and the spin. Okay, so namely this gamma k up or k down is nothing but the linear combination of C and C dagger, but later we will interpret such Bogoliubov excitations and distinguish this Bogoliubov quasi-particle excitations from the ordinary particle hole excitations in normal metals. So this is a very different excitations. The BCS Bogoliubov excitations is the excitations above the BCS superconducting ground state. Okay, so this is a superconductor, and this gamma refers to the destruction of a Bogoliubov quasi-particle, and gamma dagger k refers to the creation of such a Bogoliubov quasi-particle operator. So the Bogoliubov quasi-particle operator is made of this linear combinations of C and C dagger with a proper coefficient U, k, and Vk, and so on. And this will be interpreted as the linear combinations of particle and holes. So later we will interpret this in more details, but here you can very clearly see that this destruction operator, so-called Bogoliubov quasi-particle operator, is a linear combinations of destruction of an electron and creation of another electron. It is not just destroying an electron, but the linear combinations of destruction and creation of an electron. This is really strange. But then, since these C and C daggers are fermion operators, remember electrons are fermions, so gamma operators are also fermionic operators, which satisfy this anti-commutation rules. Here is a homework for you. You could verify that this anti-commutation rules are satisfied for gamma and gamma dagger. So you know that this C and C daggers, given the fact that C and C dagger satisfy anti-commutation rules. And let me just repeat this UK and VK coefficients, the coherence factors, one more time. Okay, so I remember I assigned this to you as a homework exercise last time, right? To show that the coherence factors are given by the square root of that complicated object. But it is easy to show because you know how to diagonalize the 2x2 matrix and find eigenvalue, eigenvectors. And we could make a plot of this Bogoliubov of excitations. So this is momentum relative to the Fermi momentum, and this is the upper branch, this is the lower branch of this Bogoliubov excitation spectrum. And in between this plus and minus branch of this EK, we get a gap. And right at the Fermi momentum, this gap is given by 2 delta. So there's a delta amount of energy gap above this in the positive energy branch, and another delta in the lower branch, negative side of energy, so that the total amount of gap is 2 delta. So this 2 delta, indicates that this is kind of a 2-electron physics, because you can imagine that once we form a Cooper pairs, which is made of 2 electrons of this momentum spins, and when we would like to create the excitations above the BCS ground state, and we need to break this Cooper pairs. So the way that we break the Cooper pair is that we need to inject twice as large as the gap in order to do so. So we will see in just a moment that all the electron states in the negative branch or minus EK branch are completely filled, fully filled with Cooper pair. That is, you have this Cooper pair completely fill up all this negative branch of Bogoliubov excitations. And in the BCS ground state, the upper branch or the positive energy branch is completely empty. There are still many states, 2 delta away from this fully filled Cooper pair states, but at 0 temperature, these states are completely empty. So there's no electrons or Cooper pairs are occupied, because all the Cooper pairs are here because this is the most stable situation that you can imagine. So we will write down this BCS Hamiltonian in terms of this gamma operator. Maybe we could just do it right now. Okay, so in terms of this gamma operators, the BCS Hamiltonian is given by this. Okay. All right, so the important point is this: the occupation number in the BCS state is no longer the familiar C dagger C or the Fermi function. Rather, this is the occupation for the gamma. Namely, the gamma is the new, I should say, the particle operator in the BCS state. So we should no longer think about the creation destruction of an electron C, because those electrons are paired up with another electron in terms of a Cooper pair. So when all those electrons are paired up in such a Cooper pairing state, then the elementary excitations are made of gamma. So gamma is our new elementary operators, not the C's, because gamma is made of, again, linear combinations for C and C dagger. So later you will see this BCS ground state, and we will come back to this point later. Okay, so this is the Hamiltonian, BCS Hamiltonian, expressed in terms of the gamma Bogoliubov operator. So you can see very clearly that this Hamiltonian is diagonalized, it's quadratic and diagonalized. Because this is written in terms of a Fermi operator, creation operators of a Bogoliubov quasiparticle, and the destruction of that operator. So it's the same form as C dagger C, but not C dagger C. It's a gamma dagger gamma. And therefore, we know that gammas are also fermions, and they satisfy the Fermi-Dirac statistics. As a result, this gamma dagger gamma is our new form of this occupation number operator. Okay, so it's not the C dagger C, but gamma dagger gamma. So as a result, let me just make a remark right here. So remark number 1, the BCS ground state is a vacuum for gamma particles. As I mentioned, when we at zero temperature, so you'll later see that there's no Bogoliubov quasiparticle excitations at zero temperature, and this gamma dagger gamma takes zero value. But at finite temperature, you have a probability that some of these Cooper pairs are broken, and this excitations are possible. And so some of the electrons will actually go up and to fill up this empty branch of this positive Bogoliubov excitation states. So you can very clearly see that the BCS ground state is a vacuum for gammas, namely there's no occupation for gamma. There's only, fully occupied Cooper pairs. So that's the BCS ground state. But at any given finite temperature, even if this temperature is below Tc, there's some percentage, a tiny amount of the Cooper pairs are broken, and they are excited, and they could actually jump into this upper branch of this Bogoliubov excitation. And the second remark is that gamma is a fermion operator. So this is the homework. And the most important remark is that the new Fermi function should be made of gamma k dagger gamma k, which is the Fermi function. So we will come back to this after a short break. What do I mean by this thermal average of this gamma occupation? And this Fermi function is somewhat slightly different from what we're familiar with in the non-superconducting states, namely this normal metallic state. So this Fermi function is a function of capital Ek, which is always a positive value, because this is a square root of something squared plus another gap square. So the sum of the two positive values should be positive, and square root of positive values is always positive. So there's no way that this Ek, capital Ek, go negative. So which makes this Fermi function slightly different from what we are familiar with. So let's take a short break, and we'll come back. We will analyze this occupation number operator made of a Bogoliubov quasiparticle. I think this is just a straightforward algebra. So mathematics is really straightforward, but the important point is the physics interpretation. And you could read this corresponding section chapters in Flansburgh, and also Kittel's second book, I think, and David Point's lecture notes. So let's look at this new Fermi functions. It's not the new Fermi function, but the Fermi function, but the energy of this fermion is different. Okay, so you could very clearly see that this Fermi function takes the energy capital Ek in the denominator, right? With the Boltzmann weight. This e to the beta Ek plus 1 in the denominator, and Ek could, it's always positive. As a result, when temperature goes 0 or beta goes to infinity, beta is 1 over kBt, remember that, right? And Ek is always positive. As a result, the denominator becomes infinity, and therefore this Fermi function vanishes. And if you look at this Hamiltonian, the BCS Hamiltonian, in terms of the gamma operator, so you could very clearly see the band dispersion that I just plotted. In the zero temperature limit, this gamma dagger gamma is actually 0, because if you take the ground state expression value of this gamma dagger gamma, you get 0, right? So the ground state energy is minus the sum of the Ek, which proves that all the electrons are from Cooper pairs, and they are occupying a negative branch because the energy is negative. But this, the sum of K, capital Ek, is a finite value because you have finite amount of particles or electrons, and therefore finite amount of Cooper pairs. And when you sum over all this Cooper pair momentums and nearby this Debye energy range. So you could show that this is your ground state energy. Remember that. And this ground state energy is negative, which makes the system stable. Remember, the stable state in the statistical mechanics is a state with the minimum energy. Okay? And this minimum energy could be achieved if you actually sum over this capital EK and take this overall minus sign. Right? So this is the minimum energy you can imagine, and which is precisely this cartoon picture is telling us. However, at any finite temperature, this gamma delta gamma is non-zero, because you can always find a small probability so that you get some Bogoliubov excitations, and such a Bogoliubov excitations are going to destroy some of the Cooper pairs, and some of the Cooper pairs may go up, and they should go up. So we will talk about this Bogoliubov excitations just a moment. In other words, the so-called particle excitations that we are familiar with in this cooling interacting, say, normal metal takes a different form. Okay, so we do not have this simply just a particle Hall excitations. Instead, to actually excite this BCS ground state, we need to break the Cooper pairs. So to break the Cooper pairs, we need to inject at least 2 delta energy cost to excite a Cooper pair. So we will come back to this in just a moment. Okay, so everything just fits. So let's look at this coherence factor, this physical interpretation of this coherence factors, U and V. So this is momentum relative to Fermi momentum, and this is V square, and another curve is U square. So this is U square, and this is K square, and this is 0, and this U square of V square. So let me just repeat this definition of this Bogoliubov operator in terms of C and C dagger. So these coefficients are called coherence factors. To correctly interpret these coherence factors, we could look at this plot. Remember, this UK and VK square are functions of this chi of k, right? So the chi of k is given by this energies relative to the Fermi energy divided by the square root of this epsilon k square plus delta square. And this epsilon k is nothing but this ordinary kinetic energy for a free electron relative to the Fermi energy. Okay, and delta is just a constant to be solved later, right? And you could, this is at 0 temperature, and you could very clearly just use the dispersion of free electron quadratic band with a constant gap delta, and you could make such a plot of this UK square and VK square. So as I mentioned, so this gamma k is made of this Hall and electron excitations with the proper coefficients UK and VK, right? So if you square these coefficients, this represents the probability of something, and which we will discuss. And that something is the probability that you form a Cooper pair, or not to form a Cooper pair. But here, this coefficient, U of k, in front of this destruction operator, which is a Hall, refers to the fact that this is the Hall coefficient, right? So this refers to the fact that this U of k square is a Hall-like coefficient, because this is a coefficient in front of the Hall, or destruction of an electron, okay, or creation of a Hall. And this is indeed the case, because this value of UK square is actually 1 when this momentum is away in the positive branch of this Fermi momentum, in the positive branch, which means that we are way above the Fermi energy or Fermi momentum, and these states are say the Hall states, because they are empty states, right, in the beginning. And therefore, you actually create a Hall when this coefficient U of k square becomes 1. And likewise, this VK square reaches the maximum value 1 way below the Fermi momentum, meaning inside the Fermi spheres, which means that you create a particle because electrons are occupied below the Fermi energy or momentum, right? So they are electron states. So, and therefore, this Vk squared should be interpreted in terms of the electron-like coefficient. And so they meet right in the middle at Fermi energy so that you have equal probability to create electron hole. So in other words, the Bogoliubov quasi-particle operator is actually made of both creating electron and hole. Okay? So it is not simply just electron hole. You create the electron or you create a hole, but you create both with different probability amplitudes. Okay? So this is really a strange, exotic type of excitation. So what kind of excitation simultaneously create a hole and electron? So this is what this Bogoliubov operator is telling us, that it creates simultaneously electron and hole with a different probability near the Fermi surface, so that they have such a profile. Okay, so we will come back to this when we discuss the BCS wave function. Okay, so you probably need some time to really think about this and absorb such a new information and understanding of this BCS states. Good, so let's just look at the BCS gap function. As I mentioned, this delta is the so-called S-wave gap, which is nothing but isotropic. In K-space, it has no momentum dependence in K-space, so as a result, this is so-called S-wave. Okay, but what is the size of this gap? Okay, so we need to solve this gap equation. And so let's just look back the definitions of the gap value. Remember, previously, this delta is nothing but this quantity that we defined earlier, which is the square of the V effective times this Cooper pair excitation value, which is the excitation value of the C K up, C minus K down. And we need to evaluate this thing. So, but what can we do? As I mentioned, the elementary excitations in the BCS state are no longer given by the operator C, rather they are given by gammas. Okay? As a result, we need to really transform all these operators in terms of gamma. So we need to transform this in terms of gamma. And remember, this gamma, dagger gamma, is this Fermi function. And since gamma operators are fermions, so if you interchange between gamma and gamma dagger, they should follow this anti-commutation relations, right? So therefore, this excitation value of the gamma dagger is given by 1 minus this Fermi function. Okay, just like this metallic states that we discussed. And then you could simply just make an inverse transformation from C to gammas. So this is the definition of a gamma in terms of C and C dagger, but we can also look at this this inverse relation between C and gammas. You could very easily see that this is something like this. And again, C and C daggers are linear combinations of gamma and gamma dagger, and with some proper coefficients. So let me just find out what this inverse relations are. So C of K, U of K, gamma minus K. Okay, so you could verify that this is the inverse relations, that the C and C daggers are linear combinations of gamma and gamma dagger with again, this proper coefficient U and V. So you take advantage of such inverse relations and you plug in this expansion value of a CC pairing, you'll get this, should be a sum over K here. Okay, so you may verify this by yourself. I will not assign this to you as a homework problem. You have enough homework problems already. But what is this? Well, this is nothing but V effective square. So this is so-called BCS gap equation. So this sets up the relation between the BCS gap and Fermi function. And remember, the Fermi function is also the function of the free electron kinetic energy and the size of the Cooper pair gap, right? Delta. Okay? So this says that to determine this gap, we need to solve this gap equation self-consistently because delta appears on both sides of the equation. Okay? So this needs to be solved self-consistently because delta appears on both sides of the equation. Okay? Remember what is chi of k? Again, chi of k is again this stuff. So both on the left-hand side and the right-hand side are functions of delta. So you don't know what delta is unless you solve this equation on both sides of the equation simultaneously. But this is not the hard problem because you know what this epsilon k is. This is nothing but the free electron dispersion, which is a quadratic band, right? And the gap is nothing but the S-wave gap, which is simply just a value across the Fermi sphere, a constant value. So delta is independent of this momentum, and V effective, again, is a constant. Remember, this is the BCS assumption that the V effective is simply just a constant, right, within this plus minus dBi range. And so you could easily solve this numerically. Even with some approximations, you can solve this equation analytically. And this is called the BCS gap equation. So if we forget about temperature 0, and then this Fermi function vanishes, remember that. And you end up by solving this much simpler equation at 0 temperature, and you can determine the size of the gap, okay, which is a function of, this your V effective and density states at the Fermi surface and so on and so forth. So we will solve this BCS gap equation in just a moment. So let me emphasize this importance of a Bogoliubov quasi-particle operators one more time. So this is our fundamental object to create or destroy a Bogoliubov energy and to actually give excitations to the BCS ground state. And this is made of particle or electron or hole excitations with a proper different amplitude or probability amplitude. And this Bogoliubov excitations actually excite the Cooper pairs to the upper branch of this Bogoliubov energy band so that some of the electrons pop up and the Cooper pairs are broken, and the gap is determined by this BCS gap equations, which will be determined in just a moment. And you can see that this gap is also a function of temperature, right? Because you could, in general, solve this BCS gap equation at any given temperature and show that when temperature reaches Tc, the gap vanishes. So you should expect this gap decreases with increasing temperature so that right at the Tc and above Tc, the gap vanishes. When the BCS gap vanishes, you go back to normal metal, and there's no gap in between this plus and minus capital E branch anymore, so that you get the usual quadratic band. So let's take a short break, 10-minute break. When we come back, we will solve the BCS gap equation at 0 temperature. Okay, so let's come back to this BCS gap equation. So before the break, we derived such a BCS gap equation at any finite temperatures. And so let's just solve this gap equation at 0 temperature first, and then we can solve this equations at finite temperature later. So at 0 temperature, this Fermi functions, functions of this capital EK vanishes, and so this is the 0 temperature BCS gap equation. If you plug in these definitions of chi of k, u of k, and v of k, and so on, and consider a constant coupling, electron-phonon mediated BCS coupling, remember this coupling appears plus minus Debye energy relative to the Fermi surface. So this is F. So electrons nearby this Fermi level relative to this Fermi level with plus minus Debye energy can form Cooper pairs, and consider this effective coupling V is simply just a constant within this plus minus Debye energy range, and this is the BCS assumption. And under such assumption, you could easily convert this summation over momentum K to integration of this energy epsilon relative to this Fermi energy mu, and you should take care of the density states at the Fermi level, and which is also a constant, and the remaining integration is ranging from minus to plus h bar omega d, and you should integrate this function over here. Remember, this delta is an energy independent constant. Okay, so you could easily cancel this delta on the left hand side and the right hand side, appearing in a numerator, and this function is easily done because this integration is very easily evaluated, and this is hyperbolic sine function. In the denominator, you could easily check the table of integration, and in numerator, this is h bar omega d by energy. So this is an analytical solution of this BCS gap at 0 temperature, but we could further simplify this hyperbolic sine function, considering a very weak BCS coupling, which means that the product of this V effective square times the density of states at Fermi level is really, really small. Okay, so we will check this in just a moment, but let's just assume that this is the very weakly coupled superconductors, which is the case for most metals, because the BCS theory is a weak coupling theory where this electron-phonon mediated electron-electron interactions, this coupling strength multiply the density of states of the electrons at the Fermi level is really, really tiny. But in more modern or more unconventional superconductors, so this coupling strengths of unconventional superconductors such as high TC cuprates and iron pnictides and other strongly coupled superconductors, this value is really large. It's greater than 1, but in the BCS theory, this value is much smaller than 1. So we will check this in just a moment. So under such a weak coupled assumption, we could ignore the smaller part of this exponential factor, which is what? E to the minus 1 over V and density of states. So forget about this term. And therefore, we get the approximate form of the BCS gap as a function of the Debye energy and the electron-phonon coupling strength and the density of states of electrons at Fermi level. And this dependence on this V times density of states is exponential form. So this is exponential relations of a BCS gap and the electron-phonon coupling, and also density of states. Okay, so if we plug in a typical value of this V times density of states, you get 1% of this Debye energy. And Debye energy is order of magnitude of 500 Kelvin, which is a very large, very high energy. But this is only a 1% of the 500 Kelvin, which means that the ordinary metals can go superconducting around 5 Kelvin, which is in a very good agreement with the observations in the experiments for ordinary metals. So most metals become a superconductor when temperature is below single-digit Kelvin, less than 10 Kelvin. 1 Kelvin, 2 Kelvin, 3 and 4 and 5 and 6 and 7 and so on. But this is a very good estimation of this, this BCS gap, and later we will estimate this Tc based on this gap. So let's just estimate this V times V density of states. Let's estimate. So V electron phonon coupling square times 1 over h bar omega d, and mq square is given by this, which is, so this Vk is actually V electron phonon. And the density of states is about n divided by epsilon f, and therefore V times density of states is about little m divided by the ion mass, number of particles, electron phonon matrix element, and h bar omega d square, which is about 10 to the minus 5, and this is about a few electron volts, 0.03 electron volts, which is about 0.1. So you could find this, estimated numbers in all these reference books, and we simply just make a very rough estimation of this V times density of states, whether this is a dimensionless quantity, by the way. It has no dimensions because V is the dimension of energy, and density of states is the number of states per energy. So V times density of states gives you no dimension. Therefore, all the dimensions must be cancelled out and follow this standard electron phonon theory. You know that this is electron phonon coupling matrix element square divided by the Debye energy. But what is mq square? So you go back to your electron phonon nodes. You find this is this combination, okay? And the V of k is simply just electron phonon potential, and you could very easily just convert this values to estimated energies at the Fermi level, and capital N is number of electrons. And density of states is number of states divided by Fermi energy, roughly speaking. So you multiply this to, you get this times this, but this electron mass divided by this ion mass, you could immediately know that this is 10 to the minus 5. But what about the square of this quantity? N times electron phonon, coupling strength is about a few electron volts, and the Debye energy is about 0.3 or 0.5 electron volt, which is about 300 to 500 Kelvin. And then you take the ratio of the two, and then 10 to the minus 5 factor, multiply together, you get 0.1. So 0.1 is much less than 1, of course. So which proves that the BCS coupling is a weak coupling theory. Just a simple exercise. And so let's just go back to the finite temperature and evaluate this, the gap as function of temperature. So remember, we derived such an equation already. So this is given by, okay, so now temperature is finite, so this Fermi function will contribute to this equation, and the gap is a function of temperature. And so we can actually simplify this equation. So delta temperature V sum over K delta hyperbolic tangent. So this 1 minus 2 times this Fermi function, can be converted into this hyperbolic tangent function divided by 2, I think. So 0 temperature is hyperbolic tangent. So you know this hyperbolic tangent function, right? It is between minus and plus 1. For temperature 0, this temperature appears in the denominator of the hyperbolic tangent function. So hyperbolic tangent of x becomes hyperbolic tangent x goes to infinity. In that limit, this hyperbolic tangent takes just 1. But in the higher temperature limit, t is large in the denominator, and hyperbolic tangent of x is approximately given by x. When x is 0, hyperbolic tangent gives you 0. Okay, so this is hyperbolic tangent function. So 0 temperature limit, this hyperbolic tangent is simply just 1, and then we go back to the 0 temperature gap equation. But the final temperature, you simply just multiply the 0 temperature gap equation by the hyperbolic tangent function over here. So let us just cancel this gap on both sides of the equation because they are the same. And then we could, again, transform this momentum sum into the energy integration. And after doing so, we have this integration. So this looks horrible, but solvable. And we know the general trend. The solution should recover the physics, namely the size of the gap should decrease as function of increasing temperature, and it should vanish above Tc and at Tc. So there is no simple analytical solution at a generic temperature, but we could get approximated form when temperature is close to Tc, because we know that when temperature is close to Tc, the gap should vanishes. Okay, and then we could make some approximations when temperature is very close to Tc and simplify this complicated integration. Let's take a short break and erase the blackboard, and when we come back, we will continue solving this final temperature gap. So again, this calculation can be found anywhere and everywhere. Theta Logica shows very detailed derivations, and Flansburg also describes in more details. So the BCS theory is a really successful theory to describe the superconductors in ordinary metals, and it is a very naive, simplified theory, but it works extremely well. So they were very lucky that they found the correct theory with the minimum complications. But we're not that lucky to understand unconventional superconductors that go beyond the BCS theory, more modern superconductors, such as cuprates and iron pnictides, where these magnetic interactions are very important to form the Cooper pairs, and the interactions are strongly enhanced. So it's a strongly coupled superconductors. So let us solve this BCS gap equations when temperature is close to Tc. Now in that limit, we know that this BCS gap almost vanishes, right? So this delta as function of temperature, when temperature is close to Tc, is almost 0. So let's just consider this as just a completely normal state where this gap vanishes at Tc, and let's just solve gap equation. And when that happened, we can determine Tc. So of course, the BCS gap as function of temperature for T below Tc could be solved numerically. Nowadays, you could use Mathematica or MATLAB or write Fortran code to solve this self-consistent equations very easily, and you will get precisely what I just plotted, that the gap should drops as you increase the temperature, and this is what gap as function of temperature, and 0 temperature limit, the gap is 1.76 kb Tc. Okay, so we will get to that point later in just a moment. And this is again the highlights or the most astonishing predictions made by BCS. And this ratio between the BCS gap at 0 temperature and the transition temperature, Tc, or thermal energy of kBTc, is about 1.7, and this prediction, the highlight of the BCS theory, and it agrees very well with many experiments. But to do so, we need to determine Tc, okay, first. And let us just determine Tc from this BCS gap equation. So now temperature is fixed at Tc, and the gap vanishes, but we still need to find Tc by solving the BCS gap equation, right? So delta is gone, right? And epsilon is the electron energy will be integrated over, and V times density of states is some fixed value. So you can do so and get the Tc as a function of all this V and density states and so on, and the Debye energy. So we could evaluate this integral in the following. So this is a dimensionless integration. So let us just define a dimensionless quantity called epsilon hat divided by 2k BTC, and I call this x, and this is integration of hyperbolic tangent divided by x, integrated over x from 0 to this Debye energy divided by 2k BTC, and this integral can be easily evaluated, and this is what? Log x hyperbolic tangent. You could do this integral from this integration by parts that you know from your first year in undergrad, right? Integration by parts in the calculus, and log s hyperbolic second square of x dx. And again, this is a weak coupling theory, and Tc or kBTC should be really small, and therefore 2k BTC is much less than the Debye energy. You know that Debye energy is about a few hundred kelvins, but this Tc is about just a single digit in Kelvin, so this 2k BTC should be way smaller than the Debye energy, and therefore this integral is given by this minus 0 to infinity, so this should be infinity. And log x hyperbolic second x dx. Well, you could check your table of integration for this integral, and you get this log 0.44, which is 1 over v density of states. As a result, you get kBTC 1.14 h bar omega d e to the minus 1 over v density of states, which is 2 h bar omega d v density of states, which is 1.14 divided by 2 times gap at t equals 0. Right. So therefore, the BCS prediction, the famous BCS prediction, is this 2 times delta t equals 0 divided by kBTC 3.5. That's so, approximately. And we know that for most ordinary metals, this ratio is somewhere between 2 and 5. So, this ratio is a universal constant 3.5, is a famous, most well-known BCS predictions, and which agrees very well with the experimental observations for many normal metals when they become a superconductor. So you can measure this gap from the density states measurement. So we will talk about in just a moment. And when their resistivity drops to 0, which is at Tc, and therefore you can take the ratio between the gap and Tc, and you get very close to this predicted value. So for these numbers, you could check all these references for details. And we don't have enough time to do all the steps one by one. So let's take a short break. When we come back, we will discuss this BCS excitations, namely the Bogoliubov of excitations and BCS gap, the wave functions. I think many results that I presented today are new to everyone. So it takes time to really digest all this new information and new calculations. So I encourage you to read our textbooks, maybe in the winter break, in the Chinese New Year, and you could think about this more thoroughly and carefully. And so this theory should really help you study this condensed matter both in theory and experiments, because you cannot avoid superconducting states in your study. So let's look at the BCS wave function, the BCS ground state. And then we will talk about their excitations. As I mentioned, this state is made of a Cooper pair, many Cooper pair near the Fermi surface. And we know very well that many pairs are formed across the Fermi surface. But what about their wave functions? Well, we know from Heisenberg uncertainty principle that if you know, say, electron wave function in momentum space, by the Heisenberg uncertainty relations, you don't know where they are, right? And vice versa, if you know, electrons in real space and you don't know what their momentum eigenvalues, but this BCS state is actually made of Cooper pairs or electron states in momentum space, right? And when they pair up, that one electrons here and will be paired up with another electrons across the Fermi surface in active site, and their spins are along the opposite directions, so you get this kind of a pairing. However, this is just momentum descriptions of Cooper pairs in K space. You may wonder where they are in real space, right? So this is the cartoon picture of the real space BCS pairing. So these electrons may be very far away from each other, but when we study their momentum states, they are simply just these pairs across the Fermi surface. But since Heisenberg uncertainty relations tells us that we don't know where they are, so in real space they may be very far away, but still sort of they know each other because they know they should be a Cooper pair. They should form a Cooper pair. Therefore, in real space, we could consider such Cooper pairs are kind of a collection of all this kind of long distance electron pairs, and they know their partner already, and then they form Cooper pairs. So the only thing we need to do is just to make a product of all this pair out, two electron wave functions, the Cooper pair. So in real space, this is simply just sum over this Cooper pair states in K space by Fourier transformations. In other words, out of the Fermi surface of ordinary metals, and you create a Cooper pair, and this Cooper pair is made of this two electrons pair up across the Fermi surface, and you create two such electron states, and then you Fourier transform this, and you sum over all possible such Cooper pair states, and this is a single Cooper pair in real space. So in other words, you don't know where they are, so they are located at R1 and R2, but when they pair up, they should pair up like this. Okay, so since this V electron phonon coupling is actually negative, so within this range of this Cooper pairing, plus or minus the bi energy, so we should expect this Fermi surface to be unstable towards the formation of a Cooper pair. Namely, this electron phonon coupling is negative, so they mediate the two electrons to form a Cooper pair. But before they form Cooper pairs, you have a Fermi surface, right? However, when they form Cooper pairs, this Fermi surface is gone. Okay, it is no longer there because they form this group of excitations. In other words, before the Cooper pairs, you have this quadratic band. But after the this Fermi, this Cooper pairs, this band is actually destroyed. So you really form. Let me just draw a nicer picture of this Fermi surface instability across this transition. K minus Kf and 0, and this is your linearized band of normal electrons, but you end up doing this. Okay, so you can imagine that I could linearize this dispersion of a conduction band in normal metallic states, but near this Fermi momentum Kf. However, when they form Cooper pairs, the finite gap, the BCS gap, develops, right? And therefore, this Fermi surface is really destroyed. How does the Fermi surface change when this gap develops, well, this is how this Fermi surface is gone. So, you can imagine that this is simply just one side of the Fermi, this band on, say, right side of the Fermi momentum Kf, and you can linearize the dispersion, all right? But then once this gap is developed, and you know very well that you have this dispersion of a plus minus a Borg of energies, capital Ek and minus Ek, and there's a 2 delta energy gap between this upper and lower Borg of bands, but just right at that point where delta becomes finite, this linearized conduction band of normal metals actually form a gap. Okay, so meaning you can imagine that this linearized band, once Cooper pair is formed, actually goes as close to this linearized curve as possible when they are away from this Fermi momentum. But when it very close to the Fermi momentum, it gets closer and closer, and this blue lines or blue curve, the Bogoliubov bands, actually deviates more and more from the linearized electron band, and so that there's no Fermi surface anymore, because we get the energy band between this fully filled Cooper pair states and empty excited states. Okay, so if this is the insulator, and you can understand that because all the electrons in the valence band are completely filled, and in the conduction bands there's no electron states. So this is an insulator, but this is not the insulator in the BCS state. It is the superconducting state. So when this gap develops, you no longer stay in the metallic state anymore. This is the new state of matter, which is a superconducting state. Okay, so let's just finish today's lectures, and we will continue the BCS states next Monday. Okay, so in any case, you can imagine that when 2 electrons form Cooper pairs, the Fermi surface is already deformed. So we don't have a Fermi surface anymore because there's an energy gap. Okay, just think about this as an insulator. You have an energy gap, divides this conduction band from the valence bands, but here this is not the conduction valence band, but this is a Cooper pair state and empty states. So the Fermi surface is unstable towards the formation of the Cooper pairs when they form. Okay, so next Monday we will finish this Cooper pairs wave functions and also the Borg excitations beyond the BCS ground state.